I'm Joshua Bardwell, and you're going to learn something today. Today I'm going to tell you about motor protocols, that is, the protocols that are used to talk between the flight controller and our ESCs. Protocols like PWM, PPM, OneShot, MultiShot, and so on. I started this presentation thinking to make a video about Dshot. I want to tell you guys about Dshot, and I know you want to learn about Dshot too. And of course I went into the background because you can't understand why Dshot is good if you don't understand what's wrong with the stuff we're already using. And you can't understand that if you don't understand the stuff we're already using, right? And halfway through it, I realized I had easily a whole video's worth of material on the existing protocols. So I know this isn't the sexy Dshot stuff that you really want, but I guarantee you the majority of you are going to learn something from this. I think it's very worth your time. I think it's very interesting stuff. Let's get into it. The motor protocols that we're talking about are all designed to communicate a throttle value to an ESC. In other words, they make the motor go faster or slower. They were originally based on servo position protocols, since that's what a receiver was set up to output anyway. If you go all the way back to the beginning, we've got a receiver. It's hooked up to some servos. The servos are hooked up to control surfaces on the aircraft, and we want the servos to go to certain positions. And instead of servos, one of those outputs is hooked up to an ESC, and that output is used to set the motor throttle value, if you will. Multirotors changed a lot of the assumptions that these devices operated under. For example, with multirotors, the receiver is no longer talking directly to the ESC. Now the flight controller is talking to the ESC. And the difference there is that a receiver is controlled by your stupid, slow, fat human fingers, right? Whereas a flight controller is a computer. It can update much faster and more precisely than your hands can. So the protocols that worked for our fingers don't work as well anymore with flight controllers and multirotors. The first protocol then to talk about is PWM, or pulse width modulation. In pulse width modulation, electrical high voltage pulses vary from 0 to 100% of the time. And so we can see down in this chart here, we've got a 0% duty cycle where the signal is never high, a 10% duty cycle where 10% of the time the signal is high, and so on, all the way to 100% duty cycle where the signal is high 100% of the time. Now, this is not the kind of pulse width modulation that is used in the RC hobby. This is a generic type of pulse width modulation that is used in other electronics applications. The type that we use is this oddball kind of PWM. Sometimes it's called PPM, but actually it's not PPM either. I'll tell you about that in a second. We use this oddball kind of pulse width modulation where instead of varying from 0 to 100%, the pulse, first of all, in PWM, the actual length of the pulse can vary. The pulse window can be defined to any value that you desire, and what matters is the percentage of time out of that window that the pulse is high. But in the RC world, or with servos, we always define the pulse as varying from 1,000 to 2,000 microseconds. So first of all, the pulse is never at 0% duty cycle. And I guess the reason for that is that the way a servo works is that the high voltage pulse is where the servo gets the energy that it uses to hold its position. So if you set the servo signal to 0% duty cycle, there would be no current flowing. The servo would have no energy, energy I guess is the right word. It would have no ability to hold its position even in the zero, whatever the zero position is, all the way to the left. So I guess that's why servos, I just made that up right now, but it sounds reasonable, doesn't it? Maybe it's even right. I guess that's why servos use 1,000 to 2,000 microseconds, because you never want the duty cycle to go so low that the servo loses authority. Okay, so there's PWM, where the width of the electrical pulse encodes some information, if you will. And then there's this oddball PWM that's used in the RC hobby, which goes from 1,000 to 2,000 microseconds. But still, fundamentally, it's the width of the pulse that matters. Keep that in mind. Now we come to PPM, or pulse position modulation. And I would argue that PPM is not actually used in the RC hobby. But you're going to see this term bandied around a lot, and I'll let you decide for yourself whether you think we're actually using it. In PPM, it is the position of the pulse within the window that encodes the value. The width of the pulse is constant and does not encode any information. So here we have an analog signal that is being sampled and is being represented either as PWM or PPM. And what I want you to see here is that when the analog value is high, the PWM pulse is longer. When the analog value is low, the PWM pulse gets shorter, right? The PPM pulse, when the analog value is high, the PPM pulse is later in the window. And when the analog value is low, the PPM pulse is earlier in the window. Now that is academically, purely, strictly speaking, the difference between PWM and PPM. And we never do this in the RC hobby. Now, strictly speaking, we're not really doing this either. As I told you, we're doing this oddball kind of PWM. So I think one of the reasons that people call what we do PPM is because they kind of know it's not PWM, so what must else, and they just look around and they latch on to some other term, right? The other place you'll see PPM used is in CPPM, combined PPM. Now, this is not a motor protocol. This is not a protocol that is used to talk between ESCs and a flight controller. But I'm putting it here because it's a term you're going to think of, and if I don't talk about it, you're going to go, well, what about that? This is not a motor protocol. It doesn't belong in this presentation. What it is used for is to communicate RC channels between a receiver and a flight controller. So you've got these, let's say you've got 8 channels coming out of a receiver, right? And way back when, if you go back to the really old days, you would have 8 wires coming out of your receiver going to 8 pins on your NACE 32 or your multi-Wii board, right? Well, that's a lot of wires, and it's a lot of pin headers, and it's really not necessary. So somebody had the idea, what if we take all of these servo signals, and instead of carrying them each on separate wires, we just sort of stack them up one after the other. Channel 1, Channel 2, Channel 3, Channel 4, Channel 5, Channel 6, Channel 7. We just take all the PWM pulses from the individual wires and put them on one wire, just one after the other, and we'll just loop through 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and so on and so on. And that's what CPPM is. CPPM is a way of taking those pulses and instead of having 8 individual wires, having one wire, and that's the main advantage of it. Notice that this is also not PPM as I described you on the previous page. I submit that PPM is not actually used in the RC hobby. Now let's start talking about some of the problems that can happen with PWM and PPM. One of the problems that happen with PWM and PPM is that there's jitter in the output. And that's because with PWM and PPM, the frequency of the motor signal is fixed and it is not linked in any way to the output of the PID loop. So let me take you through this diagram and I hope it'll make it clear what the problem is. Here is an ideal scenario that will never happen in the real world where there is no jitter. We've got a 2000 microsecond PID loop. And the reason we've done that is because the maximum frequency of a 2000 microsecond PWM signal is 500 hertz. And the reason for that, as I'll discuss on a later slide, is if the window is 2000 microseconds long, then you can't send more than one pulse every 2000 microseconds, and that limits how fast you can send the pulses, and that works out to 500 hertz. So one of the things people used to do back in the old days was they would set their loop time to match the input frequency of their ESCs. And the goal there was to cause there to be minimal jitter between the PID loop and the ESCs. So the theory was that if you had your input frequency run, let's say it would typically run at something like 400 hertz, but I've picked 500 hertz because it's the maximum possible value. So let's say it's 500 hertz. Let's say the ESC was running at 500 hertz input and the PID loop was outputting at 500 hertz. Well, in theory, then what would happen is this. Here's your output motor signal, right? And let's say that at the end of this loop, which is not pictured, the PID loop output a value of 1000 microseconds. So we see here that the signal is high for 1000 microseconds. That's half of the time because we have a 2000 microsecond window. And then it goes low for 1000 microseconds. And that whole time the PID loop is doing its thing. At the end of that 2000 microseconds, the PID loop has finished calculating and it spits out another value, which is, let's say, 1500 microseconds. Okay, fine. Now the value is high for 1500 microseconds and low for 500 microseconds. PID loop outputs the next value, 2000 microseconds. The ESC updates gets the new update, and away we go. Now that is the fantasy where everything is perfectly in sync. But in reality, the PID loop is not a fixed, perfect length of time every time. There is some difference because this is a computer, and sometimes stuff takes longer and sometimes it goes faster. So what really happens is this. The PID loop, let's say the PID loop received that same 1000 microsecond value going into this example, and so the ESC it knows that what it needs to be outputting is 1000 microseconds, or the equivalent throttle value. Okay? The PID loop is calculating, and for some reason, the vagaries of real life, the PID loop takes slightly longer to finish calculating, so that it misses the beginning of the next PWM cycle. So here, the ESC is looking at the 500 hertz signal, and it was waiting for the next update. And since it didn't receive a new update, it begins outputting the same value that it did the last time. Okay? Which is 1000 microseconds. Now, just a few microseconds into this loop, the PID loop finishes and the new value is output. 1500 microseconds. Sorry. The only time we can begin outputting that new value is at the beginning of the next window, which will be now we're outputting the new value. Right here is where this 1500 microseconds begins being output, because we missed this window. We missed the beginning of this window here. Look at that delay. And now, even if everything is perfectly consistent from then on, we're going to have that delay going forward. Here's the new 2000 microsecond value that this PID loop output. But guess what? We're busy outputting the 1500 microseconds from the previous PID loop. Okay? And that's jitter that happens in the real world because we have an unsynced output between the PID loop and the motor frequency. So now let's talk about some of the protocols that attempted to address some of these issues. And the first one we'll talk about is OneShot 125. And historians of this technology will be very, very pleased to hear me distinguish that OneShot 125 is actually a combination of two separate technologies. One of them is called Sync PWM, and the other is called Fast PWM. OneShot 125, those were invented sort of separately, if you will, and OneShot 125 sort of bundled them together, and they go together well. But a lot of people just say, oh yeah, I'm doing OneShot, and don't realize that the things OneShot brings to the table actually are separate and can be had separately if you so desire. So Sync PWM means that the exact moment the PID loop finishes calculating its new value, it is output to the ESC. There is no fixed, regimented timing. Don't we have to get a new value exactly now? We're cool, man. Whatever you got one, you send it over. And fast PWM means that we speed the whole thing up. Because that whole 2000 microseconds and 500 hertz, that's fine for our fat, slow human fingers moving a throttle, but that's not good enough for flight controllers and ESCs. So if we take a look at the example here, we can see that as soon as the PID loop is a little bit late. Do you see how it missed the 2000 microsecond window? It doesn't matter. That doesn't matter anymore. That's just there for your reference to the previous example. As soon as the PID loop is done, it spits out the new value, boop, and the ESC reads the new value. And here, again, the PID loop is a little late. No big deal. As soon as it spits out the new value, the ESC reads it. The ESC just gets the value whenever the PID loop spits it out. Now that's the synced output. And fast PWM, if you look at the difference between the previous slide and this one, here we've got the 2000 microseconds. Instead of pulses from 1000 to 2000 microseconds, we've divided that whole thing by 8. The new pulse length is 125 to 250 microseconds. And those shorter pulses allow us to go at higher frequencies, but they have another effect that I'm going to talk about later, which is that they reduce the latency between the PID loop and the motors. And I'll talk about that a little bit later. Well, we talked about OneShot, and actually what we were talking about there is OneShot 125, which is just, it was called OneShot for a long time because there wasn't anything else. But then the next OneShot came along and they had to call it something. So it was OneShot 125 because it's 125 to 250 microsecond pulse. And then we've got OneShot 42, which is a 42 to 84 microsecond pulse. And then we've got MultiShot, which is a 12.5, I think it's a 12.5 to 25 microsecond pulse. I mean, the math works out. I'm not I can't 100% verify that that's correct, but the math does work out. My only hesitation here is somewhere on RC groups, I found a post from RS2K, who is a MultiShot, or maybe the MultiShot developer, and he was talking about like a 5 to 20.5 microsecond pulse, and I don't know what that means. Or anyway, the pulse is really short. That's the gist of it. Okay, so we've got these protocols. We've got OneShot, OneShot 42, or OneShot 125, OneShot 42, and MultiShot, and they each use sequentially shorter pulses, and they can be run at higher and higher frequencies, and also they can be run either synced or unsynced. And I told you that synced was good because it reduces jitter, but unsynced can be good because it allows you to run the motor updates faster than the PID loop. And one of the things that people ask is, what's the point of running the motor updates faster than the PID loop? If we go back to this example, we can see that the PID loop is doing its crunching, its number crunching calculation here, and when it's got a new value to output, we output the new value. What's the point of repeating the old value again and again and again? The ESC got the message, didn't it? Well, that's an interesting question, and it's a question I'll address more when we get to the Dshot video, the difference between analog and digital protocols. We'll leave you cliffhanging on that one for now. In case it's not clear, there is a relationship between pulse length and frequency, and the relationship is that the maximum frequency you can have is 1 over your pulse length. If it takes you 2 milliseconds to send one pulse, then you can't send more than one pulse every 2 milliseconds, obviously. It's like if you're at work and you say, boss, it takes me 10 minutes to make a pizza. And the boss says, well, I need you to make 12 pizzas an hour. You're like, well, boss, there ain't 2 of me, buddy. Right? It's the same thing. So we said with standard PWM, with 2 millisecond or 2000 microsecond pulses, the maximum update rate was 500 hertz. With MultiShot, we can have up to theoretically 40 kilohertz. We typically practically max out around 32 kilohertz, but in theory you could go even faster than that. The maximum frequency is always limited by the pulse length, but you can go slower if you want. In other words, if we go back to this OneShot example, we can see that these pulses, we could go faster because these pulses are so short. Look at all this dead time here. We could send more pulses in here. We could fit them in. We don't have to, though. We could always go slower. And there's an interesting question to be asked of whether there's an advantage to sending shorter pulses slower. And that's another, we'll touch on that in this one and in the Dshot video. Now, this is a topic that drives me a little bit crazy because I find that people miss this distinction a lot. And I don't actually think I'm going to communicate this distinction because it seems like a really hard topic for people to get. And if people can't get it when they're presented with reams and reams of data, I'm probably not going to convince everybody of this distinction in just one slide. But hopefully I'll explain this to some of you who maybe the light bulb will go on. What's the difference between frequency and resolution? Well, frequency is how often you update the value. Resolution is how precisely you can communicate the value. Okay, if I gave you a color scale and it was red, green, and blue, and I asked you, what color is that flower? You only have 3 choices, red, green, or blue. Now you can tell me it's red, it's red, it's red. Or you could tell me it's red, it's red, it's red, it's red, it's red. You see, we've increased the frequency, but the resolution is the same. You have only 3 colors. Let's say I give you another color scale and it's got a whole palette of colors, right? Now you have more resolution. Now you could tell me that's slower or faster, right? So that's the difference between frequency and resolution. The resolution of these protocols is primarily limited by the input sensing circuit on the ESC, and I think it's fair to say all cases, essentially all cases. The output circuit on the flight controller It's pretty easy for the flight controller to make a signal with microsecond resolution. A microsecond sounds fast to humans, but to a computer, microseconds are no big deal. You could have nanosecond level, not single nanosecond, but certainly maybe 250 nanosecond level timing on the processors, on the interrupts and timers on some of these processors. So microsecond level timing is no big deal. But the input resolution is a little bit harder, and I'll leave the reasons to that to a deeper video on ESC design. The gist of it, though, is we think of the throttle as having 1,000 steps of 1 microsecond each, and that is not the case. That's an abstraction. The throttle value can vary between 1,000 and 2,000 microseconds, assuming PWM, or 125 to 250 microseconds, assuming OneShot, etc., etc., etc. But the actual input resolution depends on how precisely the ESC can measure that incoming signal. What's the actual input resolution of some ESCs in the real world? Well, BL-Heli input resolution is about 210 to 240 steps. And some of you will be surprised to find out that that's true regardless of whether OneShot or MultiShot is used. I have that from a post on RC groups written by no fewer luminary than RS2K himself. So that's as from the horse's mouth as it gets. KISS 24-amp are reported to have about 950 steps of real input resolution. That's from KISS marketing materials. That's consistent with what I've heard other places. And that's one reason why, for the longest time, people reported that KISS ESCs outperformed BL-Heli ESCs so thoroughly. As they've had about 1,000 steps of input resolution from the beginning. There are other reasons as well, like dedicated gate drivers and so on, but the input resolution is certainly one of the big reasons. BL-Heli S has an input resolution between 512 and 2048 steps, depending on which processor the ESC is using. I think that means whether it's got a BB1 or a BB2 processor, but I'm not 100% sure about that. I think those are really the only two options, so that kind of must be what it means, right? I guess so. Let's close out this video then by asking the question, does any of this frickin' matter? Right? Because when OneShot came out, people said, that doesn't matter. You're already updating at 500 times a second. Probably people like Time Cop. It sounds like something he would say. You don't need OneShot. OneShot's overkill. And other people tested it and found that it made a difference. And people said the same thing when MultiShot, 32 kilohertz, it doesn't matter. And people said the same thing about race flight. Maybe they're wrong. Maybe they're right. Which of this stuff actually matters? Does faster update rate matter? That's what I was talking about just there. Up to a point, faster update rate certainly matters. Let's say I told you were only allowed to update the motors once a second. Well, your copter would crash, right? Clearly. It certainly wouldn't be flyable in any sense that we think of it. So faster update rate certainly matters, but exactly where the point of diminishing returns is a matter of great debate. Past a certain point, faster update rates must be useless because the motors and props are physical objects and they can only change speeds so quickly. But be very, very careful about taking that argument too far. Like I said, when OneShot came out, people said the props and motors can't update 500 times a second. Why would you bother updating them 2,000 times a second? It's wasted. And it clearly turned out that that wasn't true. Something about that wasn't true. Some assumption there isn't true. I'm going to tell you what it is before the end of the video. But you're right. The motors and props can't update 500 times a second. They can't change speed that quickly. Even if you were to take into account any other sort of meta effects like averaging and error correction due to repetition and whatever, faster updates must eventually become redundant. I did some testing where I flew a copter, I tuned the copter to the almost unflyable point of oscillation. And I flew it with 32 kilohertz, 8 kilohertz, and 2 kilohertz multi-shot, and I found basically no difference that I could tell in the flight performance. So I concluded that at 2 kilohertz and above, faster update rates didn't really matter. What about input resolution? Does input resolution matter? Yes, I absolutely think it does. Remember, the flight controller and the ESC are both computers, so they can be way more precise than a human can with our fingers, right? And resolution is not really bound by the physical constraints of the motor and the prop in the same way that update rate is. Yes, the motor and prop can only change speed so quickly, but they can be asked to spin at a very, very precise speed, or RPMs, right? Realistically, there's physical constraints on how precisely we could try to spin the motors, but I don't think we've hit them with the current technology. The difference between 250 steps of input resolution and 1,000 or 2,000 steps, I think that's a difference that definitely does produce flight effects. But here's the one that I think many people overlook, and it's the shorter pulse length. Shorter pulse length is, I think, the real reason why many of these protocols perform better. Shorter pulse length means less delay between the output of the PID loop and the motor and the prop changing speed to the new commanded value. So if we go all the way back to PWM, there's a 2 millisecond delay, up to a 2 millisecond delay between the time, is that right? We have the 1,000 microsecond pulse followed by the dead time. Well, yeah, see, there's a complicated question. I shouldn't say that. Let's go back to this slide right here. How long is the delay? Here we output the new value. It's not just the length of this pulse, but we have to wait for the next pulse to begin. Yeah, so in the best case scenario, the pulse ends here, the ESC gets the new value, and we have a 1 millisecond delay, right? But here, we don't get the new value until much longer. So anyway, there's a big delay, a millisecond or so. And the point is that the shorter the pulses you get, the less delay there is between the output of the PID loop asking for what it wants and it getting what it wants from the motor and the prop. And you might say, gosh, a 1 millisecond delay, does that matter? Well, I think that it does, because I did testing, and I found that MultiShot had noticeably better oscillation handling than OneShot, even when they were both running at exact same frequency and resolution. So these were BL Heli ESCs, so the input resolution of MultiShot and OneShot was essentially the same, and they were both running at 2 kilohertz, exact same update rate, but when I switched from OneShot to MultiShot, the oscillations got better. When I switched from MultiShot to OneShot, the oscillations got worse. And that tells me that the shorter pulse length does matter. And that's consistent with what we've learned through all of the development that's been happening. Well, for me, it's mostly I see in Betaflight, but I'm sure the same lessons are being learned elsewhere. You know, one of the first things Betaflight did is let us turn off the gyro filter and go to a soft filter with less latency. And we got massive performance improvements. Lower latency has always improved flight handling. Now, the difference there, going from gyro LPF equals 42 to gyro LPF equals 188, or even turning off the gyro LPF, that was, tens of milliseconds perhaps of delay that we gained. Whereas going from a PWM to MultiShot, perhaps it gains us a millisecond or two of delay. But it still matters. I think it still matters, and I have a small amount of experimental results to suggest that it does matter. Okay, well, that is your primer on motor protocols. And the one thing that all these protocols have in common is that they're all analog protocols. All of these protocols encode the length of the pulse based on time. It's an analog thing, and it requires analog measurement on the other end, and that leads us to a whole host of other issues, and that's where we will segue into the discussion of Dshot in the next video. For now, though, hope this has been educational, and as always, happy flying.